Topology is how the components of a mesh combine to make its shape. If we want to create a circle, we could do that by making it with triangles, with quads, with an n-gon, and there's actually an infinite amount of ways that we could connect vertices together to make this shape. The way in which we arrange those components, though, determines what we can do with that shape. At the end of the day, a model is always constructed to be used for something, whether that's a game, an animation, a 3D print, a UI element, or whatever. There's so many use cases for 3D these days, but what the use case is determines how that mesh should be constructed. For example, in a game asset workflow, you want to get the most amount of detail you can with the least amount of polygons. In a visual effects workflow, polygon count is less of an issue, and you may be more concerned about its quality when subdivided and how easy it is to make changes to. In 3D printing, you might not care about the polygon count really at all, but you do care a lot that the model is one solid watertight object. So when talking about topology, it's important to realize that what might be considered good topology in one workflow or part of a workflow might be considered bad topology in another. And as you continue your modeling journey and start to specialize in a field, you'll learn all about the different requirements for your specific use case and how to tailor your modeling accordingly. Good topology has a lot more to do with the effectiveness of the end result than how pretty the wireframes are. But that said, there are still a lot of foundational things that are considered good practice all around, and those are what I want to focus on in this video. My overall definition of good topology is when the mesh components efficiently define the intended shape and can be easily manipulated. There's a lot packed into that sentence, so let's break it down. Efficient topology means not wasting a ton of polygons where you don't need them. Beginners often add loops to define details, which is a good thing, but then those loops run all the way around the model and needlessly complicate, or even worse, actively disfigure other areas. Part of learning good topology is learning how to keep your details localized and how to control the density of the mesh so that there are more vertices where you need more detail and fewer vertices where you don't. The intended shape part of the definition refers to matching your edge flow with the anatomy of the detail you're creating. If you're creating a curve, you need to have edges that follow that curve. This is pretty intuitive, but what people usually get tripped up on is the opposite, having edges that also follow a path that do not match the anatomy. This creates what I call unintentional details, which can make your model look significantly worse. Another part of defining the intended shape is supporting how the shape might need to change over time when animated. If it needs to bend, squash, or stretch, good topology supports that movement rather than works against it. The intended shape also refers to the final shading of the model. Good topology results in good shading. And bad topology, even if it looks like it creates the same shape, won't look as good when rendering. So there are some cases where you might think you have a materials issue, but the root of it is actually a modeling issue. The last part of the definition mentions easy to manipulate as one of the traits of good topology, because sometimes topology that's easy to work with can be a lot more efficient than topology that's technically better, but a giant pain to adjust. For the most part though, easy to manipulate means keeping things non-destructive and using modifiers for as long as you can, and keeping parts as separate objects so you can make changes really quickly. When you're finished modeling though, easy to manipulate can sometimes mean applying modifiers and combining objects so that the model is more performant and faster to animate. And while not technically part of topology, things like object organization, proper parenting, and having smartly placed object origins and local orientations all make a huge difference in how effectively you'll be able to model. So we'll talk about each of these best practices as we go through the course, but I also want to point out some things that are generally considered bad practice that you should try to avoid. First, broken faces. It's not as violent as it sounds, but this is what happens when you push part of a quad or n-gon too far in a non-planar direction, and the triangulation under the hood becomes obvious. In general, if you need an edge along a detail, it's better to set it explicitly. Along with this, you should also avoid concave quads. They subdivide horribly, create shading issues, and cause confusion when working with edge loops, so they're pretty much never a good idea. If you need to, split the quad into two triangles, or try to rework the area so that all the quads are convex. Really long, thin faces are also generally considered bad because they're difficult to work with, often result in bad shading, and they can cause a performance hit in render engines. Extremely dense geometry is also not great. Of course, sculpts and scans might come that way out of necessity, but to actually turn that into something usable with the process of retopology is a really important step. Also, by the way, even when sculpting, but especially when modeling, higher polygon count does not equate to higher quality. Like Einstein said, keep things as simple as possible and no simpler. Lastly, there's a term called manifold geometry, and it refers to meshes that are completely watertight and have an unbroken surface. You definitely don't need all of your meshes to be like this, unless you're 3D printing, and I certainly don't worry about having holes in my mesh or giving every single object thickness. But some other things that fall under the category of non-manifold, which you should avoid, include having inconsistent normals, having loose edges or vertices floating around the model, having exactly overlapping vertices, edges, or faces, having internally connected edges or faces, which can cause a ton of problems, and in general, any time where the back of a face is connected to the front of a face is considered a no-go. Those are all recipes for frustration, and it's best to avoid them. In this course, we'll work on practicing the good habits and getting rid of the bad ones. And in summary, good topology saves you time and energy by helping you efficiently define your shapes and keep them easy to work with.